In order to understand how materials perform, a study of their physical properties is key. So in this presentation, we will look at a common performance indicator of materials, stiffness, and how atomic structure, microstructure, and macrostructure influence it. We can look at the three major material groups on the spectrum of soft to hard or ductile to brittle. Ductile means the material deforms under load easily, and brittle means the material does not deform under load easily and will most likely fail due to fracture. Polymers are most ductile, ceramics are most brittle, and metals are somewhere in the middle. From our materials lab this week, we saw that material density, a physical property, does not correlate with stiffness of the material. This table shows specific gravity categories for different types of materials. Specific gravity is used in engineering to indicate which materials will float in water and which will sink. This is because specific gravity is the density of the material divided by the density of water. If density is greater than the density of water, it will sink because it's heavier per unit volume. If the material density is less than that of water, it will float. In the table, we can see that ceramics are in the same specific gravity classification as metals, even though ceramics are much stiffer than metals. This reinforced what we determined in our lab, that density does not correlate directly with material stiffness. So if density isn't an indicator for stiffness, what physical properties are? One of the fundamental principles of material science and specification is that if you know the material structure, you know the material properties, and therefore you know how the material will perform. There are three major areas that govern a material's properties: atomic bonding, microstructure, and alloying. Material performance looks different for the main material types in part to the type of bonding between atoms. Polymers are made up primarily of covalent bonds, which are the weakest type, which allows many polymers to deform and stretch with very little load. They also fracture easily due to the low bond energy. This low bond energy also causes polymers to break bond easily, which prohibits heat and electrical energy from traveling easily through them, and also makes environmental degradation a common pitfall to polymers. This is further perpetuated by microstructure, which we will see later. Metals bond metallically, meaning almost all electrons are shared and swapped between the atoms of one metal element. This makes for much more bond energy, but also lots of room for atoms to move and slide against each other. Therefore, metals are known to be strong and ductile. They can deform uniformly. The sea of electrons is also a reason for their great thermal and electrical conductivity. Ceramics are usually made up of ionic bonds and have very strong crystalline and molecular structures such as tetrahedral, hexagonal, octagonal, etc. This makes a bond very difficult to break because the bonds are so tightly bonded and have the maximum amount of bond energy. This makes ceramics very hard and don't deform easily, but rather they break, fracture, or crack. This also makes ceramics very insulating because they block energy from moving between their molecular structure. Microstructure looks at the material at a slightly larger scale than atomic. We are now looking at atomic clusters of atoms. Each grain or string you see are hundreds of thousands of atoms clustered together. The breaks or boundaries you see are where the bonds are cut off and a new cluster begins. Polymers are a string of molecules bonded together that are all jumbled up. You may have experienced pulling on plastic, it being very easy to deform at first, and then near fracture to deform the plastic becomes very difficult. This is especially true for elastomers. The amorphous, stringy structure makes polymers very easy to deform, manipulate, and process. It also makes them very easy to break down and reuse again, hence why many plastics are recycled. Metals have a very defined grain structure. The one shown in the image is carbon steel that has been tempered with heat. Within each bond cluster, the atoms can stretch and deform, but at the boundaries, you would have to break a bond in order to move that boundary. This means that the more boundaries there are, the more brittle the metal. The less boundaries, the more ductile. This can be manipulated by heating metals up, adding to the atomic energy, and then quickly quenching it to the configuration you desire. This is referred to as heat treatment. Ceramics microstructure is very crystalline and defined. To the same point as with the metals, ceramics typically have more grain boundaries and in longer shapes because the ionic bond clusters are less continuous due to the amount of bond energy they require. More grain boundaries as well as the smaller grain sizes means more brittle. There are some ceramics that have an amorphous structure like plastics do, namely borosilicate glass, which makes them easier to process, but this is less common. Our last point is alloying, which refers to any combination of molecules. This is to be very clearly different from composites that combine materials on the macro level. Alloying is just material combination on the micro level, microscopically. Polymers are combined to make copolymers and terpolymers. The advantage of this is combining the benefits of multiple monomers in one material. You have multiple different types of plastic with all of the benefits from each one. This is similar for metal alloying where small amounts of other metals are combined with a large amount of another. Large amounts of iron are routinely combined with small amounts of carbon, molybdenum, chromium, etc. to make carbon steel and steel alloys. This is to get a metal that has the toughness and ductility of iron and the hard, strong characteristics of carbon, the corrosion resistance of chromium, and heat treatment benefits of chromium and molybdenum. Each alloying element is going to have a specific purpose, and the amount of the alloying element added to the major material is very important for getting the properties desired. Ceramics are usually combined using an adhesive aggregate such as cement. This is because ceramics don't mix well on the molecular level due to the ionic bonds in their atomic structure. Though ceramic aggregate mixes are technically on the macro level, they are not commonly considered as composites, to not confuse them with when aggregates are reinforced with metals or other ceramic fibers. These aggregate mixtures allow for the combination of properties such as the hard, compressive stiffness of rock or silica and the adhesive moldability of cement. This mixture makes concrete.